All right, 6.4, normal approximation of the binomial distribution. This one is going to take the binomial distribution, which was a bunch of rectangles because it was a discrete distribution, and help convert them into a continuous distribution or on the normal curve to make the calculations a lot more simple or easier to work with. All right, just some things to remember about the binomial distribution. N stands for the fixed number of trials. Each N individual trial has its own chance of being repeated under the same identical conditions. There's two possible outcomes. That's why it's binomial. You got success and failure. The probability of success is known as P. The probability of failure is Q. We're looking for our number of successes, and the sum of all the probabilities is going to be equal to 1. Okay. So here is the experiment. Tossing a coin 20 times. The probability of getting heads when it's tossed. Here on the x-axis are the number of heads that are observed, and the probability of getting each. So the probability of getting 0 heads is this particular rectangle. 20 would be the same thing. We're going to figure out what the probability of tossing it exactly getting 10 heads out of those 20 tosses. So using probability that R is equal to 10, the binomial, you go 20 C10, 0.5 to the 10th power times 0.5 to the 10th power again. Okay, again, I'm using the same formula I did last chapter. You can also look in the table and figure out this probability as well. I'm going to punch in the numbers here real quick. You're probably better off going and using the table, but not a big deal either way. So that works out to be roughly about 17.6%. Okay, so what this really means is that this rectangle of 10, or the area of that particular rectangle, is 0.176. Going back to us graphing these things on the last chapter, that's basically a histogram. All right. Here's kind of the same get up as before, where you got N is the number of trials, R is your number of successes, P is the probability of success, Q is the probability of failure. Well, now, under certain conditions, and here's the conditions, if the product of N times P is bigger than 5, and the product of N times Q is bigger than 5, then R from that binomial distribution can get adjusted into a raw score of X, and then take that X score, those raw scores, and convert them into Z scores. And it's going to help us look at the Z table to find the area underneath the curve. You're going to need a mean and standard deviation. So here's the mean for a binomial distribution, and here is the standard deviation for a binomial distribution. Okay. Now, as N gets greater, the better it is and the easier it is to use this. But I'm going to show you how to do it with a particular coin project. Okay, first of all, does it even fit the requirements? So is NP bigger than 5? And does NQ work out to be bigger than 5? So 20 times probability of success. Yeah, half of 20 is 10. 10 is bigger than 5. Okay, going to be the same thing here. Just so happens that P and Q are the same. That's also bigger than 10. So can I assume that this follows the normal distribution? Yep. Our mean, which is the same NP, works out to be 10. And our standard deviation, which is going to be NPQ, is going to be the square root of 10 times the probability of failure. And that is the square root of 5. So about 2.24. Okay, so we're going to use that knowledge to make some sort of continuous or some sort of X and then Z score. A lot of information on this page, but we have to talk about what's called the continuous correction. You're basically going to have to take each of the R values given to you, and you're going to have to subtract 0.5 and add 0.5. I always like to draw a rectangle and a line. I'll show you on the next page to kind of mimic this. So maybe that would help you out a little bit. But you're going to end up adding and subtracting 0.5 kind of because the histogram and its boundaries, the class boundaries. So here we're going to figure out what the probability of R being 10 is, which we already know the answer. It's about 0.17, I think 6, using the Z table instead of R. Yeah, so if I were to do the histogram or draw that again, you've got this rectangle of 10. Well, that 10 is smack dab in the middle. Okay? If I want the actual number on the x-axis, I'm going to take away 0.5 to get 9.5, and I'm going to have to add 10.5 to 10 to get 10.5, and there's my two values of x. Okay? I've got my mean above or before of, I believe it was 10. I've got my standard deviation of 2.24. I'm going to double check that 10 just to make sure. Okay. Yep, I got 10. And I'm going to come up with two z-scores. So z equals 9.5 minus 10 divided by 2.24. And z is going to be equal to 10.5 minus 10 divided by 2.24. So negative 0.5 divided by 2.24, I get a negative 0. Remember, you round these to the nearest hundredth spots. There's one z-score. 0.5 divided by 2.24, I'm going to get the same thing but positive. So I'm looking underneath the curve, looking up the two areas of positive 2.22, negative 0.22, and I'm going to subtract them to find the area underneath that curve. So 0.22, I get 5871. And for negative 0.22, I get 0.4129. And because I want between, I'm going to end up subtracting those. Okay, and that gives me 0.1742, which is about what I got with running the formula. Okay? If you're thinking, well, why don't I just do the formula for this every single time? The reason is if you get an extremely large number of possibilities, you don't want to go and do that. So in here, we've got 22% of all patients with high blood pressure have side effects from a certain medication, and 100 patients. So that means that n is going to be equal to 100. Okay? If you include 0, that's 101 rectangles. Okay? Find the probability that at least 30 of them will have the same side effect. So at least 30 is 30, 31, 32, 33, 34, 35. Add them all up all the way to 100. You're going to end up doing that formula a lot of times. So instead, you check to see, is this an option for the normal distribution? So NP is 100 times 0.22 bigger than 5. Yeah, that's 22. By the way, that number is always the mean as well. And is 100 times 0.78 bigger than 5? Yeah, 78 is going to be bigger than 5. So yes, we can use the normal curve. Okay. Get our standard deviation here, again using the standard deviation formula for the binomial theorem. So the square root of 22 times 0.78, okay, I get 4.14. Now we're looking for the probability of R being greater than or equal to 30. That means I'm going to draw myself a little rectangle at 30. And I want 31, 32,
these rectangles. So I'm going to go from this spot on the x-axis all the way up. So if I adjust that, go halfway over, that's 29.5. So to find my z-score, I'm going to go 29.5, take away the mean, divided by our standard deviation. And I got 1.81. Okay, look at the table. I'm looking for that z-score and above. So if I look at the table, wow, that's a horribly bad drawing. My z-score is probably over there somewhere, bigger than the mean. Okay, if I look up the 1.81, I have 96.49. Okay, but that's over here. Okay, so it's going to be 1 minus that number. So 1 minus 0.9649. Okay, I got a 0.0351. So there's a 3.5% chance that the blood pressure works for at least, or the side effects show up for at least 30 of those patients. Okay. Just remember to check that NP is bigger than 5 and that NQ is bigger than 5. Always use the continuous correction. I would suggest, like I said, draw out some rectangles, put the R value in the middle, and decide which side of that bar you're going on. Page 341, 1 through 7 odds, and number 11. Okay, again, this is one of those assignments from chapter 6 that I'm going to require you to get done.